Hey class, it's Todd here, and I know a few people have had a question about Chapter 15, Problem 63. It's a pretty tricky one, so if you don't have a question on it, then I'm guessing you probably haven't got to it just yet. But anyway, I wanted to give you a few pointers, because this is a pretty tricky one. We're told that we have this car with a series of 4 people in it, and it's on a dirt road, which this has happened to me multiple times on gravel roads. At a certain speed, your car actually resonates with the speed bumps and you start bouncing up and down more and more, and there's certain speeds, if you hit just the resonance speed, you can actually maximize your bouncing up and down, and it's exceedingly unpleasant, which is why a lot of times you end up having to go slower on these dirt roads. Anyway, so we're told about this situation. We're given a distance between the bumps, so just in case you're curious what this 4.7 meters is here, we're being told that there's a bumpy road, something like this, alright, that you're driving over, and that's the distance here, so I'll call that D, but that represents the distance between any two bumps, right, which is also the distance of one cycle, if you think of it as like a sine wave, right? So, basically, we're given that information, but what we're asked is how much does the car's body rise on the suspension when the people get out? Okay, so we're being told basically, if we think of the suspension as being modeled as just one big spring, when all the people get out of the car, so, you know, the little people here, there's 4 of them, times 4, when they get out of the car actually goes up as a result of the lessened force on the suspension or the spring. So if we were to represent that with an equation, it's really just simply Hooke's law. We know that the force is going to be equal to negative kx, so if we want the x, the amount it moves up, it's just going to be equal to negative force over the spring constant k, where this force is the amount of force that was just reduced off of the spring or the suspension, so that's just going to be 4 times the weight of the people. So the question then is, what is k? If we can figure out k, then we should, in theory, be able to solve this problem. So I would guess, reading the problem, that it must have something to do with this resonant speed I was talking about and this distance d I labeled. Okay, so, well, how do we even find k? We're thinking about something that's going over some bumps and bounces. Alright, well, we're told that if we're at max amplitude, as I mentioned earlier, we're at a position where we have resonance. So if we have resonance, what that means is that the driving frequency, right, the frequency being generated as a result of our car going over these bumps, must be equal to the natural frequency of the system. So the frequency of the car over the bumps is equal to the natural frequency when we have resonance. So what that means then is the frequency that we're getting from the car is going to be equal to the natural frequency, which is just the square root of k over m. So what that means then is if we want to figure out k, we need to figure out the natural frequency. So how can we find the frequency from this information given? We're told that we're moving with some velocity this direction, right? So the car has some velocity and there's some distance between the two. Well, frequency, okay. Well, if we think about this, if we know how fast we're moving and we know the distance that we cover, we can figure out the time it takes to get from one bump to the next, right? This time here, and that time, as you can see implied by my t, this is a t, it looks a little confusing there, but the time implied by, or the time it takes to go from the one peak to the next peak, that's just the period. So if we think about this, we know that, you know, for something moving at a constant speed, distance equals rate times time, which I'm going to use the capital T since it's a period. So the period then is just going to be equal to that distance between the peaks over the speed at which we're traveling. And we know from excuse me, our other equations that there's a relationship, omega naught is just equal to 2 pi over the period. Again, that comes from the fact that period's equal to 1 over frequency, right? So what I see here is basically we can set square root of k over m equal to 2 pi times the period. Maybe I'll go back to black just so we don't get too confused. So we've got the square root of k over m is equal to 2 pi over the period t. And then here we have the period. We can plug it in. Then we can solve for k and plug that in up here. Boom. That should give us a box-worthy x value. So super tricky problem, and you'll see this on the next one, number 19 as well, the last one. I'm making you apply these concepts that we've learned to now a new situation. So give that a shot. Let me know if you have additional questions, and have yourselves a box-worthy night.